All right, folks, welcome back to the data structures and Golang series. Last time we started implementing a binary tree. This time we're going to continue. So we've finished the basic implementation. We have created a new binary tree. We have inserted and we have figured out how to print it out. And this time we're going to move on to deleting nodes from the binary tree. So there's one common method of deleting nodes from the binary tree, and it goes opposite to the way that we were inserting into the binary tree. So if you look closely at the way we're inserting, we are going from top to bottom and we are going from left to right. That's the way we are inserting. So the first item that will be inserted would clearly be the root. And next, we would insert the left child and the right child then. And next, we move on to inserting the left child and the right child for the left node of the root. And then we move to the right one. So we're going from left to right, top to bottom. That's the way we're inserting. And the obvious way to implement deletion would be to delete from right to left and from bottom to top. So we would essentially be deleting the rightmost deepest item from the tree. And so I'm just going to create a skeleton function for deletion, and I'll just call it delete binary tree. It will not take any value or any arguments at all. We will just be deleting the rightmost and the deepest item from our tree, and we can return the item that was deleted. It will be a pointer. So the first thing we need to do is we need to check if the root itself is deleted. If it is, then we just print something like the tree is empty. Let's just do a print line. The tree is empty, and we would return out. And since we are allowing, uh, I'll just return a nil there. Since we're allowing deletion of the root, we'll need to allow insertion of the root. So I'm also going to modify our function because we were not allowing insertions of the root itself. We are assuming that the root is present. That's why we are directly enqueuing it into the queue that we are creating. But now we'll need to check if the root itself is empty. If it is, then we just set the root to the newly created binary tree node. And in this, we just pass the value and we return out. So that's the first thing that we need to handle. If the root itself is empty, then we just print that it's empty and we just return out. Now, everything that we do will be pretty similar to what we were doing in our insertion. So I'll just copy over all of the operations that we're performing there, paste it in. So we'll need a queue. We will enqueue the root of our current tree. All of this stuff I will implement later, but let's just get rid of that. We'll be keeping track of a previous pointer, the parent of the rightmost deepest element. So we'll need a previous, which will be a binary tree node. Now we loop through all the items in the queue until the queue has any items. We get the current item from the queue, which would just be the queue.dvec, and we will type convert it to a tree node. Now we check if the current item has a left child. If it has a left child which is not nil, then we set the previous to the current and we insert the item into the queue, whatever the left child was. So the reason we are doing this is we only we only keep track of the previous if the current item has a left child, which means that this will definitely not be the item that we are deleting. We'll do the same thing with the right child as well. We will do a queue dot nvec of the current dot right child, and we set the previous to the current. Now, once we are done with this whole thing, we know that we are having our previous as the rightmost parent. So coming back to our previous example, so we start with the root node. our previous will just be initialized. It won't have any value. This is our current node. We check if it has a left child. In this case, it does. So we just set previous to current. Now, previous and current are both 1. Then we check if it has a right child. In this case, it does. So we again enqueue the right. We already enqueued the left. We enqueue the right now. And we set the previous to the current, which it already is. Next, in the next iteration, we devec. Now 2 will be our current and 1 is our previous. We check if it has a left node. It does. So we enqueue this. Now previous will be set to 2. Again, we do the same thing. So we enqueue this. Our previous is still set to 2. In the next iteration, our current will be 3 and our previous is still set to 2. We check if it has a left node. It does not. So we don't enqueue anything and our previous stays the same. We check if it has a right node. In this case, it doesn't. So we don't enqueue anything and our previous stays the same. Now we move on to 5. 5 does not have anything, so we don't perform any of these actions. Previous still stays at 2. 6, the same thing happens. No left child or right child. We don't enqueue anything. Our previous still stays the same. And we exit the loop. So now our previous is set to 2, which means that it's the parent of the rightmost deepest item in our list. So now we need to check if our previous has a right element. If it does, then we just set previous dot right to nil and we return out the whole function. If it doesn't, if it is already nil, then we set the left node to nil and we return out. And after this whole thing, we know that we have deleted our item successfully. So we just check if previous dot right child is nil. Let's just check if it is not nil, in which case we just set our previous dot right child to nil and we return out. Instead of returning out, we just set deleting the deleted item to right child and we set previous dot right child to nil and we just return the deleted item because our function declaration has that we return whatever was deleted. We do the same thing with the left child now. In case the right is already nil, then this would be our rightmost deepest item, which needs to be deleted. We set the deleted to the left child, we set left child to nil, and then we return the deleted. And at the end, if nothing happens, if the tree itself is nil, we won't ever come to this point. We will already be returned from here, but just to keep the typing consistent, we will return a nil there. Cool. So let's try to delete a bunch of items. And I think we can run a similar loop. So I've made this into a regular for loop, and we do it the number of times we have something in the list. Uh, we can just make this equal to because we can also delete the root node itself. Now let's try to do a go run dot. So I've realized we need to add another case here where the root is the only item in the tree. So we'll do a check for that. So we'll do if the left child is nil and the right child is nil, then we just set the root to nil. Uh, Deleted would be the root, and we just return deleted. That should fix our problem. So we see that after this point, we are starting to delete. We deleted 8, 7, 6, 5, and until our tree is empty. But after this, we are seeing a runtime error. Let's see why that's happening. All right, the problem is with the print statement. We need to have a check here as well before, because we're assuming that the root already exists in this case. So we need to check if it is nil. Then we just format print line that the tree is empty because we needed to add that case in the print statement as well. Now we see that the tree is empty, which is what we expect. Awesome. So we have implemented our delete function. The next thing we can implement in a binary tree would be the traversal. And there are three ways of traversing a binary tree. There is a pre-order, an in order and a post order way of traversing a binary tree. So let's just create another skeleton function for our traversal. So we'll call it traverse binary tree. And in this, we will provide a traversal type. So I'll just call it a traversal type. We'll need to create a type for that. So let's just call that binary traversal type, which will be an int. And we'll have a bunch of consts here, which will be pre-order, binary, iota, in order, and post order. And this is what our type will be provided as. Now we'll have a switch case here, which will be the traversal type that was provided. We'll have a case for each of these. So first we'll have for in order, I'm sorry, pre-order. Let's just return out of this for now, and we'll create a case for all of these. And post order. And for each of these, we will have a function. We will have a function for each of these traversal types. So we can have a pre-order traversal, and this will take a node, which will be a binary. It will be a binary tree node, and we'll get to the implementation in just a sec. And we will call each of these in this function. And for the node, we will just pass the root node of our tree. Traversal basically means that we are going to all of the nodes of the tree and we are performing some operation. We'll just perform a print operation for now. But essentially, the aim of the traversal is to just reach each node of the tree and do something with the node. So pre-order traversal starts from the current node and visits the left subtree and then visits the right subtree. So we would first visit one, then we would visit two. Now, since we are providing pre-order for this whole thing as well, we would now visit five. And since five does not have any other children, we would now visit the right of the current node, which was now six. After moving back, we visit the right subtree of one, which would be three. So that's how pre-order works. In order is where we first visit the left subtree, then we visit the current node, and then we visit the right subtree. So it would be something like visiting two, but since two also has a left subtree, we go there. So we go to five, then we go to two, then we go to six, then we go to one, then we go to three. In post order, we visit the current node the last. So we go to the left subtree, we go to the right subtree, and then we go to the current item. So in this case, we would first go to 2, but 2 also has a subtree, so we would go to 5. So 5 would be our first item, 6 would be our next item, 2, 3, and then 1. So that's post order. These are the three ways that we can traverse any given binary tree. So, and we're going to implement all of these three ways. So in pre-order, what we did was we'll need to print. I think I'd rather have a printf here, a formatted print. Uh, let's just print whatever value we got for the node, and then we would recursively call this function. We would pass the left child, then the right child, and before all of this, we check if the node that was provided was nil. If it was, then we just return out of it. And this is what a pre-order traversal would look like. We first perform the operation with the current node, then we visit the left subtree and then the right subtree. And we can essentially just copy and paste this whole thing into our other functions, but we would just do this in the middle in order, and we would do this at the end in the post order. And that should cover our traversal. So before we start deleting, let's just have a traversal phase. So we would traverse in all of the different ways that we have provided. and we would call all three of these for, and that should be enough. Let's try to run this. All right, so traversal pre-order, we start with the pre-order, and this is our tree at the moment. So we started with one, which is the current node. We moved to the left subtree, and then we moved again to the left subtree. We moved again to the left subtree. Now we move to the right subtree of 2. Then we move to the right subtree of 1, which is 3. We move to the left subtree of 3, which is 6, and then the right subtree of 3, which is 7. And we did the same thing with in order. We started with the left subtree. I've just realized while copying and pasting, I'm just calling pre-order for all of our functions, and that's why our output is a bit weird. So I'm just gonna fix that real quick. Now let's try to call our function. Okay, now this makes sense. So we go to the left subtree, but since 2 also has a left subtree, we go to that, we go to 4, and 4 also has a left subtree, which is 8, so we go to 8. Now we perform our print operation on 8. Then we go to 4, we perform print operation on 4. 4 does not have a right subtree, so we just move to the parent again. We print 2, then we print 5, which is the right subtree. Uh, because in order performs right after we have performed the operation on the current. Then we move to the parent again, we perform print of 1, then we move to the right subtree. Now, right subtree also has a left and a right subtree, so we perform print on 6, then 3, then 7, which makes sense. Post order, we start with 8, we go to the parent again because it does not have a right. We go to the parent again, but this has a right subtree. So we perform the operation on the right and then on the parent, which is why 5 was printed first and then 2. Now we move to the parent, which is 1. 1 has the right subtree again, so we perform the operation on this. 2 also has a bunch of children, so we perform the operation on this. So we first print 6, then 7, then 3, then 1. All right. So this was our video. We performed a delete operation and we learned how to traverse a tree properly. So I hope you learned something from this. Thank you for watching. Subscribe to the channel and I'll see you in the next video.